This is the tutorial on evaluating credible evidence for judgment and decision making and advanced social psychology classes. So this tutorial will cover several things. We'll first talk about traditional indicators, which includes general factors, validity, factors that matter less, and then we'll move on to open science specific indicators, which include open science practices and reporting. And under this, we'll also briefly talk about effect size. And then we'll talk about methods. Then I'll go over 2 articles as examples for looking at open science specific indicators. Then I'll briefly talk about fallacies and then direct you to resources that we have for this topic. I'll briefly cover about the traditional evidence pyramid first. So this is what a traditional evidence pyramid looks like. We have background information and expert opinion at the very bottom, followed by case series and reports, case-controlled studies, cohort studies, randomized controlled trials, and then we have systematic reviews and meta-analyses at the very top, where it's considered as filtered information, and all of these are considered as unfiltered information. Background information and expert opinion is considered at the very bottom and not very high quality because it's summaries or opinions without empirical evidence. For case series and reports, it's based on a single person or case study without controlling for variables in the case. So this needs more empirical evidence. For case-controlled studies, it's based on a single case or case study where some variables are controlled for. For cohort studies, it's a study where a larger sample of participants is focused upon. And for RCTs, randomized controlled trials, a larger sample of participants where participants are randomly assigned to a condition to lower bias. For systematic reviews and meta-analyses, this is the synthesis of all published literature about the factor or effect. And a little more up-to-date one would be the pyramid on the right, where on top of systematic reviews and meta-analyses, we have clinical practice guidelines. So this one are recommendations for clinicians based on best available research evidence and practice experience. So based on traditional evidence pyramid, we should actually be looking at clinical practice guidelines or meta-analyses or systematic reviews to find credible evidence. There are actually general factors that we can check throughout primary studies and observational studies also, along with meta-analyses and systematic reviews. The first factor I'm going to introduce for you to check would be bias control. Would the article have pre-registrations prior to data collection, and is it available and is it shared? Pre-registration registers hypotheses, methods, and/or analyses before it is conducted. This prevents practices such as p-hacking, which is analyzing your data in many different ways and only reporting significant ones. Publication bias and harking. Harking is when you present a post hoc hypothesis, so hypothesis which is generated after data analysis, as an a priori hypothesis, which is a hypothesis generated before data collection and analysis. Harking stands for hypothesizing after the results are known. We also have conflicts of interest, so whether authors and affiliates directly benefit from research outcomes. If they do directly benefit, then you need to consider whether certain practices may have been done to ensure that the outcome is significant or not significant. You also have to check the setting in which the experiment was conducted. Was it in a controlled lab setting, or was it a field setting? Findings in a well-controlled lab tend to be much stronger because it's operated or tested in the most ideal environment possible, compared to real-life setting where there are a lot of extraneous variables present or affecting the experiment. You will also have to look at ethical approval, whether or not there's a clear indication of this. You could also check peer reviews. To check this, you should go to the journal website to learn more about the submission process. If the paper is reviewed by a panel of reviewers who are experts on the topic, and the article was published, then it passed quality control for that journal. However, what makes a peer review more credible will be that the review, that is, the reviewer's comments and the author's replies, are made publicly available for all to read, and that the reviewers can be identified. This allows others to know what the comments the reviewers made, why reviewers made the comments, how the authors addressed the comments, and better understand the changes or improvements the paper underwent. You could also check whether there is a publication bias. A publication bias is when significant effects are often published more as it's deemed more interesting. And because it's published more, this leads to effects being perceived as stronger than they actually are. To check whether there's actually publication bias, you should find a meta-analysis or meta-analyses with publication bias checks and adjustments. When you're going through the meta-analysis, check whether there are null findings and whether everything is positive. If there are null findings, that is, some publications do not support the effect, then it suggests that the effect doesn't consistently work or does not work in certain environments or situations, as the world has randomness. Even with effects, we expect variance and distribution. In other words, not everything works all the time. If everything is positive or the effect is consistent, it suggests that the effect may exist or works as expected. You should also check publisher quality, such as whether they are predatory or legitimate. A publisher is considered predatory when they are exploitative and prioritizes self-interest and are non-transparent. For example, they accept articles quickly with little to no peer review or quality control. This does not attest to the credibility of publications. And they might also not have clear policies on retractions, corrections, or plagiarism. And there are actually a lot of other characteristics. So predatory publishers, because they churn out articles really quickly, they can spread misinformation really easily. Some university websites or academic websites, like Open Access, provide some key characteristics of predatory journals. So do take a look and determine whether the article you're investigating is published in a predatory journal. If not, then it's likely that the publisher is legitimate. Transparency is another general factor that you could also check. For example, are the materials, data, and code publicly available and not available upon request or blocked access? This ensures that the materials and the data analyses can be reproducible. If these are reproducible, then it can usually attest to the credibility of the paper because the results and the materials can be replicated. You can also check whether there are any updates about the article you're looking at, whether there's any retraction or correction or expression of concern. And you can do this by using Google Scholar or Zotero's Integrated Retraction Watch. You also need to look at validation, whether the paper has been validated by others who do not have a conflict of interest, so third-party individuals who are not directly involved in the research. Whether the author's citations or references are credible is also another general factor that you could check. If indirect or secondary citations, so indirect or secondary citation is used, then it's very possible for the other author to misinterpret the findings or results. So you should be very careful when reading points that are secondary citations. It's better to read the original author's work. What we mean by secondary citation is that when an individual cannot access the original author's work and cite the source or information based on another author's interpretation. On to validity. The content from these slides are from Simin Vaziri's lecture, and her video is linked below, so make sure to take a look if you would like to know more. The first validity I'm going to talk about is construct validity. Are you measuring what you say you're measuring? This is always important. If you're not measuring what you're measuring, what does the results mean in the end? So make sure to ensure that the article that you're reading has valid measures. Then we also have internal validity. This is whether your causal claims are valid or not. When you are testing for differences between existing groups or between manipulated groups, internal validity is very important, as these tests are often used to establish causality. When you're testing between existing groups, it is difficult to establish causal relationships, such as X causes Y. And this is because there are possible threats to this relationship. The first one will be reverse causality, where instead of X causing Y, it's Y causing X instead. There's also the threat of third variable, where Z causes X and Y. For testing for differences between manipulated groups, causal relationships can usually be established, but similar to testing differences between existing groups, there are also possible threats. So a threat could be confound, where the manipulation of X also affects other variables. So if X can also affect variable A at the same time as variable Y, is it really a causal relationship? There's also selective attrition, where participants drop out in non-random ways. If participants are dropping out specifically due to something, then perhaps there might be something wrong with the research. So in this case, can causality actually be established? So it's a good idea to consider these threats when you or the publications are making causal claims. On to external validity. Are your claims about generalizability valid? So when authors are generalizing to a population, external validity is very important. And there are two types of external validity. we have population validity and ecological validity. Population validity is when we want to know whether it's representative of the population. This is quite difficult to achieve, and usually in research we use convenient samples. It's accepted and quite common, but there is a risk that the results are unrepresentative because, for example, you do convenient sampling from a psychology major, and usually in psychology majors it's female dominated, so it's not representative for males. For ecological validity, it's whether the setting or design mirrors how it actually would be in a real life setting. If the design doesn't reflect how it actually would be in a real life, then would the findings be representative of how it actually works? So when you're checking the external validity of a paper, make sure the sample is representative and the design is as close as a real life setting as possible. Alright, on to statistical validity, whether or not your statistical conclusions are valid. This is going to be a very brief, watered-down version of what statistical validity is. You should be learning or have learned this in depth in Introduction to Quantitative Methods in Psychology or Research and Quantitative Methods in Psychology. Alternatively, if you want more information or a refresher, please feel free to watch Samin Vaziri's lecture. The link is provided below with the timestamp. For statistical validity, a conclusion is made based on whether you reject or do not reject the null hypothesis. To do this, you need a p-value. And p-values mostly matter for confirmatory analyses, not exploratory. Confirmatory analyses is when you want to test specific hypotheses. And for exploratory analyses, you usually do this when you don't have hypotheses and you just want to collect and analyze data to see what patterns may emerge. And this is usually conducted when a topic is not well known. Back to p-values. Whenever you reject the null hypothesis based on a p-value, you have a chance of committing a type 1 error, which is called false positive. So when you reject a null hypothesis, that is actually true in the population. When you do not reject the null hypothesis, there is a chance of committing a type 2 error, a false negative, which is when you fail to reject a null hypothesis that is actually not true in the population. So in other words, whether you commit a type 1 error or a type 2 error hinges on the p-value. To keep a p-value valid within a study, the following things should be done. You could pre-register data collection and the analysis plan. This is usually for confirmatory analyses. This prevents changes after data collection. You could also report unexpected or unplanned results as exploratory, where a new hypothesis is generated after data collection and data analysis, not presenting a post hoc hypothesis, which is a hypothesis generated after data analysis, as an a priori hypothesis, which is a hypothesis generated before data collection and analysis. Again, this is called harking, hypothesizing after the results are known. Finally, you could also report all studies and statistical tests conducted. This allows you to be transparent about what you have done for the study. On to the factors that matter less. The first one we want to cover would be impact factor. Impact factor is the annual mean number of citations of published articles in the last 2 years. Usually, journals with higher impact factor are seen as more important. However, this figure does not indicate research quality and does not demonstrate whether the journal adopts open science and transparency practices, which is more important in determining research credibility. Impact factor indicates citation impact. What you should look at instead would be the transparency and openness promotion factor. This is the transparency and openness promotion website, and this assesses journal policies for the degree to which they promote transparency and reproducibility, which are considered as core scholarly norms. And as you can see here, it says that it's a metric that reports the steps that a journal is taking to implement open science practices that are based on the core principles of the scientific community, and is considered as an alternative way to assess journal qualities. So the journals are actually rated on 8 standards, and you can see the standards here from the summary table. The 8 standards are used to increase transparency and openness, so it includes things like data transparency, materials transparency, study pre-registration, and replication. And it also explains about what is considered not implemented, level 1, level 2, and level 3. For top factor, the higher the rating, the higher the journal promotes transparency and reproducibility. Similar to impact factor, a high top factor doesn't indicate high research quality. It indicates the extent to which journal policies facilitate the evaluation of research quality. In other words, the degree to which they comply with the top guidelines. Now let's take a look at some journals. Let's say we want to look at a journal about social psychology. Maybe the British Journal of Social Psychology. And as you can see here, it provides a brief description of the journal and gives you the total level or rating of the journal selected. In this case, the British Journal of Social Psychology got a rating of 10. And as you scroll down, you can see the breakdown of the categories or ratings for each of the 8 standards. For data citation, they got 0. There's no mention of data citation at all. Data transparency, they got 1. The article states whether data are available and where to access. And what the journal wrote is that all papers need to be supported by a data archiving statement, and the data set must be cited in the methods section. So no mention of analysis code and transparency, or materials transparency, or study pre-registration, or analysis plan pre-registration. They got 1 for design and analysis, reporting guidelines. Authors are encouraged to adhere to recognized research reporting standards. Okay. Replication, the journal accepts registered reports. Registered reports and publication bias accepts registered reports. And open science badges, the journal offers 3 open science badges. Let's check another journal, Meta Psychology. Again, a brief description of what the Meta Psychology journal does. And we see that Meta Psychology has a rating of 27. And from a quick skim through, it seems that Meta Psychology does promote transparency and openness quite well. They got a rating of 3 on most of the 8 standards and only got 2 for the study pre-registration and analysis plan pre-registration and open science badges. Then we have reputation of scholars. It's more about the process and evidence, but sometimes we do need someone's reputation or expertise. So for example, statistician is likely to be better at statistics than a non-statistician. Then we have citation count. A high citation count generally means that the paper has a high impact on the field and high subsequent impact on later research, directions, or theories. So this does not provide an indication of whether open science methods are used. We also have H-index and I-index. H-index is the number of publications an author has been cited by other authors at least the same number of times. For example, an H-index of 55 means that the author has published at least 55 papers that have been cited at least 55 times. I-index, or the I-10 index, is the number of publications an author has written that has been cited by at least 10 sources. So for both H-index and I-index, these indicate how much the author has published and how much their publication got academic attention. Some people use these two as a measure of quality, but actually, these are measures of community awareness, publications or authors being noticed, and further engagement. Being cited can be a good thing or a bad thing. It could be bad because others do not support the article findings or methods, so they cite you in their paper. Or good because the community found the findings or theories helpful, so cite it to discuss more. So this is just a poster demonstrating things that indicate the publication may not be as credible as believed. You could use this as a checklist. Some of these are already mentioned in the previous slides. For example, for number 3, we already mentioned conflict of interest. Then there's also number 11, where there's unreplicable results. And number 12, non-peer-reviewed material. Number 7, unrepresentative samples used was also mentioned, where results may be specific to a particular sample only and not applicable to the population. And number 10 was also mentioned, selective reporting of data, reporting results which supports the conclusion of research and ignoring others that do not. Open science is about transparency and accountability. For example, hypotheses, methods, and analysis plans are registered before conducting data collection and analyses. Conflicts of interest are declared. Procedures, materials, and data are freely available and accessible. And it's also about ensuring research rigor by having reports peer-reviewed and the peer review history made public. These things help with the credibility of publications. And building on the traditional evidence pyramid, for open science research, the evidence pyramid looks something like this. Research that has not been pre-registered and data and materials are not archived would be at the very bottom, called the status quo research. They are considered not worth mentioning, as it's hard to determine whether the research is credible or not. Then above status quo research, we have exploratory open science. Information from these articles should not be used to inform policy because it's not pre-registered and because it's exploratory, investigating something that isn't well defined or something that's poorly understood or trying to establish a theory or effect. Publications considered as exploratory open science will be slightly more credible as data and materials are archived. Then we have confirmatory open science up the pyramid. This would be relatively credible because it's finding evidence for or against a hypothesis. It's pre-registered and data and materials are archived. Others can check the credibility of the paper, but there's an issue that there might be publication bias. Then next, we have registered reports. This is considered quite credible as it's pre-registered, data and materials are archived, and it's immune to publication bias because regardless of the significance of whatever is being tested, the journal has already agreed to publish the paper. Then near the top, we have the meta-analysis of registered reports. It's considered credible, it's pre-registered, data and materials are archived, and it's a meta-analysis. It synthesizes all the available research. And for this one, it's synthesizing registered reports, which are immune to publication bias. So this will very likely accurately capture the significance or effect of whatever is being studied. Then we have a registered report, meta-analysis of registered reports with open data, code, and search. So this is just essentially make a meta-analysis of registered reports itself, so it's immune to publication bias. Then at the very top, Feely has suggested a continuously updated registered report, meta-analysis of registered reports. So this is pretty self-explanatory with automatic updates to a registered report meta-analysis. On to the indicators, which are mostly more open science related. The first one will be about the theory or hypothesis. You should check whether it is plausible, is it falsifiable, can it be disproved, and can it be tested using common or proposed methods. And is it possible for the effect to exist? And whether contrasting findings from literature are addressed and possible bias in cited studies is acknowledged. On to open science practices. First one I'll talk about is pre-registration for conformity quantitative research. So having a pre-registration is all right, but the most important thing is that the open science practices need to be done well. So there should be falsifiable, testable hypotheses and clear description of analyses and predictions. Then we have open materials. So materials can be accessed and readily available. Then we have open unidentified data or open synthesized data that has been vetted by a trusted third party to have the same statistical properties. Then we have open, well-commented, reproducible code. So readers can easily know what the code means or what they represent. There's also direct independent replications that you should check. Are there any failed replications? If they are, it might suggest that the effects might not exist. Is there a number of successful direct replications? If there are, it suggests that the effects may exist. And whether there are any replications with mixed results. If there are mixed results, it suggests that the effects might work in certain areas or under certain environments. whether there are conceptual replications. So conceptual replications address the same research question and hypothesis or hypotheses, but are using different methods. In other words, the variables measured and are manipulated using different strategies, but the idea remains the same. Direct replications are when the exact or very close methods are used as the original article. If conceptual replication is found in effect, it suggests that the effect may exist as different methods are used, and a similar finding was found. If there is no support at all, the effects might not exist. So think twice if the research isn't transparent or these open science practices are not done well. Again, keep in mind the open sciences practices have to include these, and they have to be done well to be considered as credible. Just having A to E does not necessarily mean that it's credible. The quality might not be the best. Then we have reporting. You need to have a reasonable, realistic effect size. I'll talk a bit more about this in the next slide. Then we also need humble, careful, cautious reporting. So no over-exaggerating effects found or its practical or theoretical significance. If whatever has been found has been exaggerated, it might be the best to think twice as to why it was reported this way. Just to briefly talk about effect size. So effect sizes are used for interpreting results and quantifying the magnitude of effects in research. That is the size of a difference or strength of a relationship. There are two types of effect sizes. The first one is raw effect sizes, and the second one is standardized effect sizes. Raw effect sizes have the same units as raw data, so for example in grams, whereas standardized effect sizes no longer have a unit and are standardized to be able to have a universal interpretation. For standardized effect sizes, conventional benchmarks have been suggested, such as Cohen's d benchmarks, where 0.2 is considered as small, 0.5 as medium, and 0.8 as large. However, these labels are actually relative. The size of an effect and how it should be interpreted depends on several factors. It depends on the discipline, the context of the research, and the research method and goals. These three factors should always be considered over Cohen's suggested benchmarks. Effect size measures depend on and differs across these factors. So you should not follow these benchmarks unless there is likely a very strong publication bias and that it's acknowledged that the benchmarks are overestimations. You always need to take into account the context of the study. To do this, you can check meta-science papers. For example, for social psychology, Lovakov and Agulina suggest a Cohen's d of 0.15 as small, 0.36 as medium, and 0.65 as large. And for depression studies, it suggested that 0.27 is small, 0.53 is medium, and 0.86 is large. When you compare it to the general benchmarks proposed by Cohen, you can see that there is quite a difference. In other words, if you see a social psychology study with a Cohen's d of 0.4, don't simply consider it as small based on Cohen's guidelines. but refer to the average effects found in social psychology. In this case, a Cohen's d of 0.4 is actually considered medium. Be very careful when referring to benchmarks to quantify the magnitude of an effect. Note that domain-specific averages are often updated, so you should always check. Back to open science indicators, we'll now look at methods. So there should be full transparency of methods, procedures, and outliers, exclusions of conditions, measures, and participants. And what we mean by transparency is that authors are open and willing to share enough information so that the same study could be, in theory, or in actuality, exactly repeated. We should also check whether there's a high power, which is sometimes associated with large samples, and if NHST, which stands for null hypothesis significance testing, so statistical inference method, where an effect or factor is tested against a hypothesis of no effect or relationship. That 1, there are no indicators of questionable research practices, for example, like p-hacking, and you can check this using tools like p-curve or z-curve, or using the p-checker. Number 2, the p-values are accurate in line with the statistics reported. Number 3, the statistics seem accurate. For example, no different degrees of freedom across statistical tests run on the same sample without explanation. Number 4, the report went through third-party assessment using tools like Grim, Calc, Excel, Sprite, etc. These tools could verify the statistics in publications, whether they are consistent with the given sample size and the number of scales. Then we have to look at random condition assignment. Methods and assessments are replicable, generalizability, choice of control, multiple comparisons accounted for and adjusted for. These help increase the quality of research. Then there's power analysis, method for power analysis, and reference from previous study. This is so that others, if they wish to replicate or check the publication, could rerun the power analysis to understand it. A reference from a previous study provides a starting point of where the new study could base their power on. So think twice if the methods seem weak, doesn't seem appropriate for the research question, or might be missing any of these, or did not do very well on these. I'm now going to move on to the examples for looking at open science specific indicators. For the first example, we'll be looking at Ecker et al.'s paper, and this paper was found from entering the keywords psychology, misinformation, and pre-registration in Google Scholar. If you want more information about using Google Scholar search and Zotero, please refer to the YouTube link provided on this slide. This was a previous tutorial given by previous TAs. The search for this paper was narrowed down from 2015, since we want the most recent papers for the coursework. We would prefer if you found the recent papers in the last decade. Ecker et al.'s paper is the third one here, and as we can see, it is a registered report, which should promote transparency and open science. For this paper, I'm just going to focus on the open science practices and reporting part, and for the next example, I'll look at the methods indicators. Now let me just switch to Ecker et al.'s paper. Okay, this is Ecker et al.'s paper. It's called You Don't Have to Tell a Story, a registered report testing the effectiveness of narrative versus non-narrative misinformation corrections. Let's focus on the open science practices and reporting that we covered in this tutorial. The first thing under open science practices is pre-registration. So if we go through the abstract here, it says that it has 3 pre-registered experiments. Okay, sounds good, but is it available to view? I've gone through this paper before and have highlighted the key things. You can go through this paper more thoroughly in your own time if you want to extract more information. But to quickly search through this, we want to know more about pre-registration. Right. Yeah. This says that data was pre-registered at OSF and the data are available on OSF also. Let's go to the data analysis part. And as we can see here, the data is pre-registered on OSF. There's the pre-registration experiment file. Yep. And it seems like they pre-registered the methods, how they're going to recruit participants, power analysis, their materials going to be used, and their methods. They also included their survey files. All materials is available at OSF. Let's click on that also. And then seems like there is a pretty clear procedure. And their data analysis plan was also registered. Yep, exclusion criteria, outliers, type of data analysis they will run, two-way mix ANOVA with factor condition and delay on inference scores. Yeah, let's take a look at the survey files. Let's take a look at the data. Okay, it's in Excel format. It clearly states which experiment each data file belongs to. Okay. Seems pretty good. It's non-identifiable. You don't know who actually answered what. And we won't know, for example, what QD2 means, but it seems that they have a data key. Yep, so then QD would be responses to questions relating to claims, A to D. Q1 is the memory question scale, 2 to 6 are inference questions on 1 to 11. Then QD would be relating to claim D. And if it's D2, I guess it's a question on inference questions on a scale of 1 to 11. So the data key is actually pretty clear as to explaining what each column means. Move back to the original site. Also has the registered stage 1 report. I won't go through this because this is pretty lengthy, but it seems good. Then we have the survey files for all experiments in PDF and Qualtrics export format. Since these are available, it'll be easy for others to replicate their study. I'm not going to go through all of it because, again, it's also pretty lengthy. It's 39 pages. Then pre-registrations, I think we already looked at that. So just let me switch back to the PDF. Okay, so we just went through the OSF links provided on the article, and we saw that they did a pre-registration. They definitely have open materials. We saw the data, and we also saw the QSF files and saw the materials they use in the registered report / pre-registration. We saw that the data is unidentified, but we actually don't know whether or not it's third-party vetted. So, yes, but unsure if vetted by third party. Then we have open, well-commented, reproducible code. I couldn't really find this on the PDF and the OSF, but I might have missed it or something. But for now, I'll just say there is a code book available for understanding the data, but there's no data analysis code, and we are unsure what software they use to do data analysis. Did they use SPSS, Jamovi, Stata, or R? So code book available. Seems clear, but no data analysis code. Whether there are direct independent replications. From just going through the paper, it doesn't mention anything about independent replications. So for this would require additional research of whether there are independent replications. Okay, on to reporting. Whether there's reasonable or realistic effect size. Let's check out the effect sizes. Okay, experiment 1. Materials, procedure, results. We ran a two-way mix ANOVA, significant main effects, partial eta squared of 0.246, 0.015, 0.014. On to experiment 2, 0.014, 0.002, 0.011, 0.005, 0.002, 0.003. Okay, experiment 3. Okay, from just taking a quick look, They conducted mixed two-way ANOVAs, and they reported partial eta squared as their effect size measure, and is reported across the 3 experiments, which usually ranges from 0.002 to 0.246, including both significant and non-significant effects. It seems quite reasonable and realistic, but you'll have to check using the effect size guide or finding meta-science papers of exact benchmarks for the effect sizes. Alternatively, if we can't find anything about partial eta squared in meta-science papers, you can convert partial eta squared to Cohen's d or Cohen's w. More information on how to do this or about converting effect sizes is also available on the collaborative effect size book or online. So I would say yes for now here. And we need humble, careful, and cautious reporting. When I had a thorough read of this paper, I thought that the reporting was impartial and careful. So in my opinion, I would say that they did humble, careful, and cautious reporting. So in order to decide this, you have to read the paper carefully. And I'm not going to do this in this tutorial because it's going to take quite some time. Let's move on to example 2. We're going to be looking at Chow et al. 2024. We're going to focus on methods, open science indicators for this paper. Whenever you're reading your articles, you should do all open science indicators, such as open science practices, reporting, methods, theory/hypothesis, but due to time constraints, I'm just showing only some parts for each paper. And also, disclaimer, I'm just going through the papers really quickly in this tutorial, so I might have missed something, or the authors actually did some open science indicators that I might have missed. So just let me know if that happens. This paper used the same keywords as example 1, inputted psychology, misinformation, and pre-registration. And I found this paper on the second page. Again, I narrowed down the search to 2015 for recent papers within the decade. And Chow et al.'s paper is The Persuasive Effects of Social Cues and Source Effects on Misinformation Susceptibility. And as you can see here, they also did pre-registration. Let me just now switch quickly to the PDF. For Chow et al.'s paper, they have 5 experiments. So for the purposes of this tutorial, I'm just going to focus on experiments 1A, 1B, and experiment 2. First, what we want to look at is whether they have full transparency of methods, procedures, and results, particularly the outliers, measures, and participants. Let's just search for outliers now. Nothing about outliers. Let's check the methods. If I remember correctly, the methods are near the end. Yep. Methods. All additional measures and scales collected as a part of each study can be found in the supplementary information. Table H. So I'm not going to read through all of the methods here. I think you can take a look yourself. But when I was going through it, I thought that the methods and actually the procedure was quite clear as to what exactly they did in each experiment. And it's quite descriptive. The measures used are also quite clear. Let's see if I think they also mentioned something about pre-registration. Yep. So present studies, we pre-registered hypotheses in study 2. One of these studies, the second, study 4 was pre-registered. So we'll just focus on 1A, 1B, and 2. Let's check this link out. This is the pre-registration page. Data collection, no data have been collected for the study yet. The hypotheses seem to be pre-registered for 6 of them, and the DVs are specified, and how many conditions there are stated. The analysis plan is indicated, so one-way ANOVAs with planned contrasts for hypotheses 1 to 4. For outliers and exclusions, for transparency, results will be reported with and without exclusion of participants who did not pass the manipulation check. Sample size. Taking into account the previously found effect size of comments on fake news judgments, we conducted an a priori power analysis using G-power. Power analysis using an alpha value of 0.05, power of 0.9, shows that to detect an effect of approximately D equals 0.3 required a minimal sample size of 690 participants. Going back up, the date this was registered is on May 20th, 2021. Back to the PDF. When going through the paper, I thought the methods and procedures were pretty clear and were quite descriptive. And just going through the pre-registration just now, it is publicly accessible and it should have been done before data collection. So it was registered on May 20th, 2021. And the outlier criteria was mentioned on the pre-registration that they will exclude anyone who did not pass the manipulation checks. And the measures are described in within the manuscript. I think they also mentioned something about supplementary. Supplementary information. The online version contains supplementary material available at DOI. Right, let's check for supplementary information, supplementary tables. This is the supplementary document, and from a quick look, it seems pretty descriptive. Tells you about study items used in study 1A. Pretty clear about the source name and the content, category it fell in, and whether it was factual information and misinformation. For study 1B, again, it's also quite clear about whether the source name is hidden or shown, and the content. In study 2, it's the same source name, what the content actually is, category, and whether it's misinformation or facts. And quickly looking at the other studies. the materials seem pretty clear. And for analyses with exclusions applied, they did provide it, which is good. So you can compare the ones with and without exclusions. Then psychological scales and additional measures collected in each study was provided. Okay, so it says here, need for cognition. Participants were asked to complete a 6-item need for cognition scale. Unfortunately, due to data collection error, only data for 5 of the 6 items were collected. Might be better if they actually stated which item was unable to be collected, but this might be in the actual main manuscript, so we'll have to check. But generally, I think it's material-wise, it's quite descriptive for someone to replicate using the same materials. Back to the main manuscript, let's also check whether there are any deviations from the pre-registration. The keyword deviation didn't have anything pop up, so I guess there aren't any deviations from the pre-registration. Let's summarize this once more. Materials and procedures seem pretty clear after a thorough read, and it's pretty descriptive. The pre-registration is publicly accessible and done before data collection, and the outlier criteria is mentioned on the pre-registration, and the measures are described within the manuscript and also provided in a supplementary, which is quite descriptive, and no deviations from the pre-registration is noted. So I think this is generally done, but needs another check for the deviations. Okay, on to high power and power analysis, method for power analysis, and reference from previous study. Let's go to study 1A first. For study 1A, the data was collected as a part of a larger intervention experiment on social cues using the Bad News platform. And data for study 1A consisted of data from the pre-intervention questions. So no a priori analysis was conducted. It's part of a larger intervention experiment. And the final sample was 7,788, which is actually a very large number. So it's definitely high-powered for study 1A. For a between subjects design with 3 conditions. For study 1B, a power analysis indicated a minimum sample size of 609 participants was necessary to capture small effects, D equals 0.3, with 95% power at an alpha level of 0.05. Okay, so this means that they conducted an a priori power analysis with a specified effect size. And they, in the end, recruited 628, which is above the minimal sample size, which is good. Seems high-powered, or at least met the minimum requirement to capture small effects. Let's look at study 2. For this study, a power analysis indicated 470 participants would be sufficient to detect a small effect size of D equals 0.4 with 5 groups, an alpha level of 0.05, and 95% power. The final sample was 730 participants. Again, they recruited above the minimum sample size, which is good. That means that it met the minimum requirement to detect a small effect size. But it's curious where they found the specified effect size, or where they base their effect size on. So for this one, it's a cohency of 0.4, whereas the one in study 1B is 0.3. It might be more transparent if they explained why they chose these specific values for the studies. So yes, for this one, high power conducted power analysis were possible, but unsure where the effect sizes came from. Specified in pre-registration that they used G power. On to there are no indicators of questionable research practices such as p-hacking when using tools like p-curve or z-curve, and p-values are accurate in line with the statistics reported. To do this, we will need to extract the statistical values from the paper. So again, we are focusing on studies 1A, 1B, and study 2. If we go back to study 1, if you remember from reading the pre-registration, we'll just focus on hypotheses 1 and 2 because of limited time. And again, we are focusing on studies 1A, 1B, and 2. And since they are conducting ANOVAs, we need degrees of freedom 1, degrees of freedom 2, the F ratio, and the p-value here. So we have one set of data, two sets here, and the third set here for hypothesis 1. Then on to hypothesis 2. This is only relevant to studies 1B and 2. So we have the fourth set of data here and the fifth set of data here needed to be inputted into p-checker. This is p-checker. We have to enter our relevant statistics here. So it does provide you with a base or instructions so that you can easily follow it. What p-checker does is that it lets us know whether the p-values are correct or whether there's excess significance, and we can check out the p-curve. But right now, what we want to know is whether the p-values are correct. For Traberg et al. Study, this is what we should have just extracted just now. And if we look at whether or not the p-values are correct, here it states that the percentage of p-values that are incorrectly rounded down out of the 5 sets of data we inputted is 0%. And we look at the detailed results for each statistics. Study 1A for hypothesis 1 is fine. So is study 1B and study 2. But for hypothesis 2, study 1B, it is red, and what it's saying is that there is a reporting error. Either the p-value has been incorrectly rounded down or incorrectly rounded up. And the error direction states that it's bigger. And if we look at the p reported here, p equals 0.37, the actual p-value, p-checker calculated for us, is a value of 0.365. So that means for study 1B, the p-value was rounded up to be conservative. So as you can see here, the p-values for each of the sets of data was actually calculated for us, and we can compare it to the p reported. But since p-checker does it for us, we don't really have to check unless it's highlighted in red. I'm going to refresh this just to show you the demo data and how it looks like for whether or not the p-values are correct. So this is the demo data originally there. P-values are correct. And for the paper ID for number 7, it's in red. So it's the reported p-value is p less than 0.01, and the calculated p-value is 0.012. So it's in red, there is a reporting error, and the error direction is smaller. What it's telling us is that the paper reported the p-value smaller than what they actually calculated. Then if we go further down, we see this paper called C, D, and E. It's also in red, again similar to the one we looked at just now. It says there is a reporting error and the direction is smaller. The paper reported a p-value of less than 0.01 when the actual p-value calculated is 0.036. And if we go back up, you can see that the percentage of p-values that are incorrectly rounded down are 2 out of 14 of the studies, which is around 14%. From using p-checker, it seems like there are no indicators of questionable research practices. No p-values have been incorrectly rounded down for hypotheses 1 and 2. So again, we're just looking at hypotheses 1 and 2 for this example. Then on to the next point, that the statistics seem accurate. As mentioned previously, in this case, we would be checking whether the degrees of freedom are consistent. Since they are conducting one way between subjects and ANOVAs, we need DF1 and DF2. So DF1 will be calculated by the number of groups minus 1, and DF2 will be the total number of cases minus the number of groups. For study 1, as mentioned previously, the total number is 7788, and there are 3 groups in total: high condition, low condition, and control condition. So this is N, K is 3. If we calculate it by ourselves, then it should be DF of 2 and 7785. 8 minus 3 is 5. Let's extract of the degrees of freedom first before we moved on to the actual DFs used. S1B, this should be A. N in this case for study 1A is 628. And K is also 3. High condition, low condition, and control condition. For study 2, N is 730. And K is 5 conditions in total. If we calculate it, DF1 would be 2, DF3 would be 628 minus 3. In this case, it would be 625. For study 2, the calculated one would be 4. For DF1, DF2 would be 730 minus 5, which in this case is 725. Okay. Let's go on to look at the reported values. Study 1A for hypothesis 1 reported 27785, which is a match. For H1 reported study 1B, it's 2625, which is a match. Then for H1 for study 2 reported 4725, which again is a match. Moving on to H2, study 1B, 2624, 2624. This seems inconsistent because it should actually be 225. Seems like one participant was excluded here, but not explained why. Or it might be a typo. Then on to study 2, reported 4725. This is a match, so seems good. Then for hypotheses 1 and hypotheses 2, the statistics currently do not seem accurate because one of the DF is inconsistent. Okay. Next, let's move on to whether or not the report went through third-party assessment using tools like Grim, Calc, Excel, Sprite. This might be a bit too hard to look at, so I think I'm just going to check whether there's assessments. Okay, discussion, okay, Grim, Calc, okay, Excel, Sprite. Tools. Seems like there's no mention of this in the manuscript, but I might have missed something. And if I recall, this wasn't also mentioned on a pre-registration, so no mention of this. Okay, random assignment to conditions. For study 1A, as automatic randomization to conditions was not possible on the platform, participants were assigned to a condition by selecting a number from 1 to 3, which then redirected them to one of the 3 social cue conditions, which were high, low, and control. Okay, given that they were using a large intervention experiment using the bad news platform, they definitely can't do a random assignment. It was based on participants selecting a number. It's good enough in this case. Then for Study 1B, participants were randomly assigned to conditions high, control, or low. It might be better if it was stated how they were randomly assigned. So let's take a look at procedure. Once they were redirected to the Qualtrics platform, they were shown information about the study and provided informed consent prior to starting. Following this, participants were randomly assigned to one of three conditions. Yep. So Qualtrics is pretty good at randomly assigning participants to conditions because you can specify the number of participants, whether or not you want them to be equally assigned to the conditions. So I would say this was probably done well. Then study 2. Yep, again, Qualtrics platform, participants were randomly assigned to one of the 5 conditions. I guess this is met, particularly for studies 1B and 2, not really applicable for 1A. Methods and assessments are replicable. I think this was pretty good because we saw the supplementary. It was quite descriptive as to what the content was, whether it was categorized as misinformation or actual facts, and Twitter handles. And the DVs and the scales were also provided in the supplementary, which is pretty clear. Then generalizability. Let's take a look. For study 2, participants were recruited on Prolific, and 1B also recruited via Prolific. 1A, they used the Bad News platform. So Prolific is an online crowdsourced program, and they allow anyone all over the world to do experiments, do questionnaires online. So anyone is available to do the questionnaires Trauberg et al. Conducted. But while they reported, for example, the gender distribution, the education, their political orientation, whether or not they had Twitter, but they were missing reporting the ethnicity, which I don't think they actually asked here. Yep, not for study 1B. Let's see study 2. Again, gender, education, political orientation, social media. Okay, no ethnicity. Let's check study 1. Age, gender, education, political orientation, social media. Demographics. So no ethnicity for studies 1A, 1B, and study 2. In this case, it might be a bit difficult to know whether or not their findings are generalizable across the world. It might be that Prolific is more popular in Western countries rather than Asian countries. Okay, choice of control. For study 1A, they were manipulating social cues, so high, low, and control condition. And for the control condition, the headlines did not employ any misinformation strategies, and the content of these were chosen to reflect global news events. This is a pretty standard control, which is good. There's no social cue manipulation at all. Then on to study 1B, social cue manipulation, influence perception of social consensus. Okay, high condition, likes and retweet numbers were set to be greater than 1,000 and comments greater than 100. Low condition, values were set to less than 10. In the control condition, these measures were cropped out. Yes, that's a good choice of control, because they wanted to see whether a high number of likes and retweets, low numbers of these, could affect perceptions of social consensus and reliability of misinformation. On to study 2. 5 conditions. They manipulated explicit versus implicit, and direction for endorsement versus discrediting. For the control condition, there were no social cues at all, which is pretty standard because they wanted to assess whether explicit and implicit social cues influence perceived reliability of misinformation. Multiple comparisons accounted and adjusted for. When I was going through this paper, I didn't notice anything about this. So let's say, for example, corrections or correction. Nothing. Bonferroni, one of the popular correction methods. Nothing. Comparisons. The interaction between source credibility with post hoc comparisons showing So there were post hoc comparisons in this study, but from a quick look and me reading this, I couldn't find any mention of controlling or accounting for multiple comparisons, but I might have missed it. So I'll just put a question mark for here now. On to fallacies. I'm not going to go over all of these fallacies as there's a lot. You could go through this in more detail in your own time, and the website to this poster is provided below. So fallacies are errors in reasoning, which would undermine the logic of an argument. And some of the common ones that may occur in real life would be the straw man. Straw man is when you misrepresent someone's argument to make it easier to attack. For example, an instructor says that their course is hard, and the student takes this to mean that the instructor is failing everybody in class. Then there's black or white fallacy. This is when there are two statements. One must be true, even when there are other possibilities. For example, you can join a society to find university friends, or you can be alone during your university years. This doesn't account for other possibilities, which could be that you can find friends in lectures, gyms, or halls. Then another common one would be the anecdotal. This is when you use a personal experience to make an improper conclusion of a topic, such as a dog bit me once, so all dogs must be aggressive. When determining the credibility of a publication or just reading a paper in general, Pay attention to whether or not you're making any of these fallacies listed, or whether the authors of the article you're reading are making any of these fallacies. These are the resources we have available for evaluating credible evidence. The first is the Evidence Collaborative book. You can take a look and you can feel free to contribute. When you contribute, please make sure to include your name in the relevant area. We also have an Assessing Study Credibility coding sheet. This was made by the MPhil/PhD students at HKU, and it's very helpful. It also contains Feely's ratings of how important those suggested factors are. And the lower the number, the less important it is. There's also the effect size book, and you can refer to this book if you're looking for benchmarks or domain-specific averages. You can see the note here that effect sizes are domain-specific, so be very, very careful when you're interpreting them. And here are the references used for this tutorial. And credits for the icons used.